Hello and welcome to our webcast. Today's topic will be selecting air distribution devices for critical environment applications. My name is Jim Oswegen. I'm Chief Engineer for Titus, and I'll be presenting today's program. I'll be joined later by Randy Zimmerman, who's also a Chief Engineer, and Mark Costello, who's Product Manager for Grills, Registers, and Diffusers. As a panel, we will answer any questions you may have at the end of the program. HVAC air distribution systems are required to play many different and sometimes unique roles in critical environment spaces. ASHRAE Standard 170 defines the minimum air change per hour required for dilution of various types of critical environment spaces. Pressure control varies by space type as well. For example, operating suites generally require positive pressure, while laboratories generally require negative pressure. The standard also identifies filtration requirements for contaminant removal. Humidity control may be required with some infectious diseases. During this presentation, we will discuss diffuser selection when using mixing and when using non-mixing outlets. Hospitals and laboratories have many unique types of spaces. Each space has different air distribution requirements depending on human comfort, patient health, and contaminant and disease control requirements. We will now investigate some of these unique requirements. There are many spaces in hospitals and laboratories where comfort conditions are controlled by conventional air distribution devices, transitional areas, patient check-in areas, waiting rooms, and office areas where human comfort is the primary objective can be conditioned by traditional directional type outlets. To better understand air distribution, let us begin by viewing the characteristics of air being discharged into a room through an air outlet device. Within a short distance after the air leaves the device and is distributed into the space from an outlet, it begins to entrain air from the space into the jet. This creates an expansion of the jet at an angle of 11 degrees in all directions. The various applications of airstream can be defined by what is happening in these four zones of expansion. To better understand these four zones of expansion, let's look at them individually. The first zone maintains a constant velocity and typically extends approximately 1 to 2 duct diameters from the face of the outlet. The goal for laminar flow diffusers is to have an extended first zone. In the second zone, the jet begins to mix with room air, causing the jet to expand. Linear outlets typically have an extended second zone. The third zone is where most of the induction occurs. This zone has the most effect on room air velocities and room air induction. The fourth zone is relatively low velocity. The performance in Zone 4 is a function of CFM. The performance is independent of outlet size. Radial diffusers operate in Zone 4. Ventilation of healthcare facilities is guided by ANSI/ASHRAE Standard 170-2008. We will refer to the limits prescribed in this standard throughout this presentation. Laminar flow diffusers, defined by ASHRAE 170 as non-aspirating diffusers, are designed to be used in an operating room above a surgical table and staff to provide a sterile field during surgery. The reduced effective area at the face and internal baffles are used to create an airstream with velocity averaging 25 to 35 feet per minute of clean air and a minimal entrainment to create a sterile field. While I would recommend that HEPA filter be located in the supply air duct ahead of the outlet to allow servicing the unit without contaminating the operating room, the HEPA filter can be installed inside the laminar flow diffuser for servicing through the face of the unit. Non-aspirating outlets show little change in velocity, placing them in Zone 1 throw category. The 35 foot per minute air velocity is important because the differential temperature between the patient's body and the room generates natural convection currents from the body at about 35 feet per minute. These natural convection currents create a defense system for the patient during surgery. A higher velocity airstream will increase the chances of contaminants being driven into an open wound. Where higher velocity air jets can be deflected by objects in the airstream, these low velocity airstreams tend to flow around the objects and redevelop on the other side. ASHRAE Standard 170 requires that no more than 30% of the primary supply diffuser array area be used for non-diffuser such as lights, gas columns, etc. Now we will discuss some specific applications for critical environment diffusers. We will spend the bulk of our time covering Class B and C operating rooms, but we'll also cover some design consideration for clean rooms as well. The number one critical environment space in a hospital is the operating suite. Infection control is a primary concern in these spaces. Staph infections are the fourth leading cause of death in the U.S. Many of these infections originate in the operating room. It is critical to keep any contaminants in the space out of the open wound. Staph infections growing on a bone are the most difficult to cure. Contaminants can be transmitted to the patient from surgical instruments, but also may be transmitted from the skin particles flaking off the exposed surfaces of the surgical team. A typical operating room layout has a patient on a 3 foot by 6 foot operating table surrounded by the surgical team. Other stationary equipment such as lighting, IV poles, surgical gases, and video monitoring equipment, as well as tables with required surgical instruments, will also be accessible to the surgical team. For Class B and C operating rooms, Standard 170 prescribes the area of primary supply diffuser array. We shall call this the sterile field. Shall extend a minimum of 12 inches beyond the footprint of the surgical table on each side. This diagram illustrates a minimum field of 5 foot by 8 foot, but notice that some of the surgical instruments may still be outside the sterile field. By enlarging the sterile field to an array of 8 foot by 8 foot, the extended area allows more room to encompass the surgical instruments. Standard 170 requires a minimum of 2 low sidewall return or exhaust grills be spaced at opposite corners as far apart as possible, with the bottom of these grills approximately 8 inches above the floor. This will allow the contaminants in the room, which are heavier than air, to be exhausted from the space. Additional return or exhaust grills located near the ceiling to remove lighter than air contaminants are not required, but may be a good idea, as we will demonstrate a little later in this presentation. In this video, we are demonstrating an 8 by 8 sterile field over the blue operating table. A small area near the center of the field has been blocked off to simulate an obstruction such as a light located in the airstream. The smoke shows a low velocity piston of air with even distribution throughout the pattern. What the smoke video does not show is the entrainment of room air into the pattern near the ceiling level. Manufacturers of non-aspirating diffusers typically use a perforated face with a low 13 to 23% free area face. This results in a low velocity discharge airstream of clean air across the sterile field. A lower percentage free area is higher in pressure loss and sound, but provides a more even distribution. So let's look at the physics of the air discharging the diffuser. As the air from the plenum chamber is pushed through the openings in the face, a vena contracta occurs which further reduces the effective free area of the discharge hole. Thus, at the center of the hole, the effective area is further reduced to approximately 50% of the open face area. So what does this mean? Let's do the math. A nominal 24 by 48 inch face with 13% free area would have a net free area of about 1 square foot. At 220 CFM, the discharge velocity would appear to be 220 feet per minute. But with a further 50% reduction of effective free area caused by the vena contracta, the area is actually reduced to a half a square foot and the discharge velocity is increased to 440 feet per minute. Even if you don't believe that the vena contracta occurs, that would still leave a discharge velocity of at least 220 feet per minute. So, how does this velocity slow the air down to 30 feet per minute, required by ASHRAE Standard 170? The answer is that these high velocity discharge jet entrain room air near the ceiling and into the pattern, which slows the jet down. As we discussed earlier, a jet of air released into a room expands at 11 degrees in all directions. This expansion is a result of room air being induced into the pattern. The net result is during the first 12 inches from the face of the diffuser, room air is induced and slows the air jet down to 30 feet per minute uniform velocity. This elevation view, illustrating the air flow from the non-aspirating outlets to the surgical table, illustrates the air pattern as we would expect it to happen. The reality is that the lightweight airborne contaminants near the ceiling can be induced and carried into the air supply to the patient. In this smoke video, we can see how the lightweight smoke, when introduced into the room outside the sterile field, is induced into the pattern along the ceiling and is carried to the patient in the center of the airstream. To further complicate matters, Standard 170 allows for some of the sterile field to be occupied by surgical equipment. It is possible that this obstruction could be near the perimeter area. This plan view shows that if the sterile field were obstructed near the perimeter, the induced contaminants could be carried further toward the middle of the airstream. In this smoke video, we illustrate how contaminants from the outside of the sterile field would carry further into the center of the operating area if an obstruction at the ceiling were placed near the perimeter. This plan view shows that using an air curtain around the perimeter will prevent airborne contaminants outside of the sterile field from being induced into the airstream at this upper level mixing zone. While a full air curtain would project air down to about the knee level for contaminant control, the most important part of the air curtain is the first 2 to 3 feet down from the ceiling. Most of these lightweight contaminants will enter the airstream at or near the ceiling. To meet Standard 170 requirement, all that is necessary is the sterile field extending at least 1 foot from the sides of the operating table. As we discussed earlier, this would be about a 5 by 8 foot array. To prevent having the necessary operating instruments being located outside the sterile field, we recommend extending the sterile field to an array of 8 by 8 of non-aspirating diffusers. For extended length surgeries, there is an increased risk in transmitting infection to the patient with these minimum standards. The most difficult staph infection to cure is when it attaches to a bone. So, add surgical suites doing bone surgeries to the critical list. For these critical surgery suite rooms, we recommend the use of an air curtain for added patient safety. This smoke demonstration shows that the smoke introduced into the room outside of the air curtain is not allowed to enter the sterile field surrounding the patient. Including the air curtain into the operating room suite design is the best way to ensure the safety of the patient during extended length or critical surgeries. Another type of critical environment application is in rooms with fume hoods. It is important to remove any harmful chemicals and toxins from these critical spaces. Safety for occupants in these applications is very different from an operating room. Typical laboratory environments require diluting the room air with high volumes of clean air while maintaining low velocities in the occupied space. For laboratory applications, the desired air distribution pattern is hemispherical. This means that the air is distributed both outward and downward from the diffuser, creating an even distribution of low-velocity air throughout the space. While air is distributed outward from the sides of these diffusers, it is usually desirable to discharge the air vertically at the end of the unit, not allowing the air to spread. This high-volume, low-velocity air pattern occurs in Zone 4 of our expansion chart. There are several styles of diffusers available for radial flow applications. The Tritech design is a fixed deflection available either with a one-way or a two-way discharge, which mounts nearly flush with the ceiling. The Versatech design discharges air in the center face through an optional perforated, non-adjustable, center vertical discharge, or adjustable vanes in the center, while the outside vanes are adjustable to produce either a tight horizontal ceiling discharge pattern or a deeper hemispherical air pattern. The Radiatech is a fixed hemispherical air pattern, optional one or two-way, with a face extending below the ceiling surface. The Radiatech is also available with an optional room-accessible HEPA filter. An additional application for these type of outlets is in TV studios, where we have high loads in the space and need a lot of air, but at the same time we want low velocity in the space. When designing a space with fume hoods and hemispherical pattern diffusers, it is important to avoid having high velocity air jets pass across the sash of the hood. If an air jet passes over the sash at a velocity higher than the entrance velocity, it will draw contaminants from the hood and redistribute them into the space. One design strategy is to place hoods perpendicular to the diffusers to avoid these high velocity jets. This elevation view shows that it is also necessary to have a vertical air discharge at the end of the diffuser to avoid high velocity jets being directed toward the hood. One of the characteristics of these fourth zone jets is that throw is not affected by continuous length of the air pattern in the same way that it affects standard linear diffusers. The throw for two units mounted end to end is the same as one unit alone. In summary, hospital buildings give the designer an opportunity to use many different styles of outlet to match the requirements for occupant comfort and safety. Use these design considerations to make the best choice. For Class B and C operating suites, a positive pressure between 0.01 and 0.3 inches must be maintained in the room. Laminar flow over the patient and surgical staff is required. Enlarging the area to ensure that all surgical instruments are within the sterile field is recommended. The maximum velocity of the airstream in the sterile field is 35 feet per minute. This is to prevent contaminants from being forced into an open wound. Standard 170 requires minimum of 20 air changes per hour in the operating room, of which a minimum of 4 air changes per hour must be outdoor air. While not required by Standard 170, we recommend including an air curtain in the design where critical surgeries are performed. For laboratories with fume hoods, use maximum induction radial air pattern diffusers. Avoid air jets directed toward the hood sash where velocities are greater than the sash intake velocity. Mount the diffuser with a discharge air pattern perpendicular to the fume hood to avoid short-circuiting. Radial diffusers can be mounted as close as 24 inches from the hood. The panel will now answer your questions.